Okay, this is Mr. Peterson, and I'm covering the notes for section 1.1. This video will cover parts A and B, and I'll do this subsequent parts of this notes on other sections of the video. Okay, so we're going to start with a concept of a function. So a function is any relationship in which the input value generates at most one output value. So if I have a number coming in, I can only associate with that number at most one answer. The input is usually labeled X, and the output is usually labeled Y, but sometimes it's f of X. And you may have seen this in the earlier course in Algebra 1. Your teachers probably said, if you see an f of X, just replace it with a Y. That's not exactly right, but it is a fairly good place to start. Okay, so this first example here says if a specific person's name is the input and the output is at person's current age, excuse me, the relationship is a function since we don't assign more than one current age to a person. So your teacher may not want to tell you their age, but instinctively you know the relationship is a function, since only a crazy teacher would claim to be several ages at the same time. So I'm going to show you that it's a function by showing how ridiculous it would be. If Mr. Peterson told you, yeah, that's me, I'm the input. I'm 35 years old, and I'm also 59 years old, and I'm 63 years old. Something triggers in you and said that can't be true because this is supposed to be a function. You're only supposed to be one age at a time. And as of the recording of this video, that middle value is 59 is the close one. Actually, it's the right one. I am 59. Okay, example 2. We're going to turn this around a little bit. The input is going to be a day of the year, and it's supposed to be somebody's birthday. So we know that if you pick a day of the year, you might find somebody that has that birthday. So I've just arbitrarily chosen the 8th of March. And 3 people raise their hands, Jake and Sue and Tanya. Well, that's not a function because we know that one birthday can go with several people. In fact, if you consider the population of the world, each birthday has to go with many hundreds of thousands, if not millions of people. So that's not a function. One input generates more than one output. This first example up here, that was the wrong way to think of it. It should be one person with one age. Okay, now let's start applying this to mathematics. So what I have here is a graph with 5 points scattered on it on example 3. And these 5 points have different x and y values, but you'll notice that the pair here that are in a vertical line above each other, they have the same x value, but different y values. So the input x equals 1 gets paired with both 4 and -2, and that means that this is not a function. So this leads us to what's called the vertical line test. And if you want to abbreviate vertical line test, V period L period T period, you're welcome to do so in my class. And the vertical line test, stated in sentence format, says that if any vertical line passes through more than one point on the graph, the relation is not a function. So it's kind of a see if it passes or fails the test here. So I'm going to show you, I'm going to draw a vertical line over here. And what I'm going to do is take that vertical line and sweep it across. And so far so good. As of this point, it hit just one point. But when I move it over to here and it hits those 2 points, I know that this scattering of points is not describing a function. Okay, so let me show you how the vertical line test looks like in practice. What you're going to do is just draw vertical lines. So here's an example. And maybe I can get it to actually be vertical. If it hits 0 places on the graph, or I'm going to move this over here a little bit. Now I'll draw another one. Only 1 spot on the graph, and let me move this a little bit so it actually hits just 1 place. You're okay so far. But as soon as it hits more than 1 spot, for instance, that spot and that spot, this just failed the vertical line test. And so we're going to write that. Fails the vertical line test. And you write down here that this is not a function. Function can be abbreviated FCN. All right, this next graph, and my little program doesn't do the arrowheads. We can see that if we draw these vertical lines here, I'm just doing it by hand here, each of these vertical lines just hits that graph just once at a time. So for instance, that last line I drew just hits there, and the first line I drew just hits there. So each time you draw a vertical line, no matter where you draw it, the most you'll ever hit that graph is once per time. And that's how it passes the function. This passes the VLT. The vertical line test, you should know what those letters stand for if you choose to use the abbreviation. So this is a function. You say, yes, it's a function. Okay, so we're going to continue here. And what this is a short catalog on page 2. We're still on part A. Of some of the functions you might be familiar with, or you should be. Linear equations, and they start out like this, y equals x. That's what this one is. You could change the slope by saying, for instance, 2/3 for a slope, and then maybe go up 6 units up, and that would change the slope of the line and where it crosses the y-axis. But you can see that it passed the vertical line test. So these diagonal lines that you've been doing for many years are all functions. Parabolas are also functions. If you draw these vertical lines, they only hit, 1 per time. And so this passes the vertical line test. And the key characteristic of the formula here is it's got a squared in it. So you're looking for that squared when it's a parabola. Incidentally, the adjective form of parabola is parabolic. So when you're describing something as having that shape, you say it's a parabolic dish, for instance. Okay, the next little box here has the V-shaped graphs that we've seen a couple of. They're always associated with absolute value signs, and they also pass the vertical line test. I'll just do 3 or 4 lines there, vertical lines. And each of those vertical lines hits once, 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 once. Now, it can also miss. I think I showed that on a previous example. But if you ever have a vertical line that hits the graph twice, then it fails the test. So this one passes. And horizontal lines, and they look like this, y equals, and this one looks like it's going to be y equals 1 here. Yeah, y equals 1. Now, if I had a line up there, it'd be y equals 2, or 4, I mean. Okay, so you just picture drawing all these vertical lines here, and none of them cross more than once, so that one is also a function. Okay, vertical lines, by the way, themselves, if you had a x equals 3, okay, let me try that again. I had the wrong tool. X equals 3 would be a vertical line like this, and then if you drew a vertical line right on top of it, it'd hit more than once, and in fact, it hit millions of times. So vertical lines like x equals 3 are not functions. All right, shifting gears here, part B talks about a certain notation called set notation, and I probably should put in there set builder notation because that's what it's actually called. You'll see that down below there. And interval notation. And we're going to start with the familiar. We're going to start with the way you would describe these points points here that are shaded in elementary school. So we have a border of 6, and the shading starts at 6 and goes to the right, but it's actually not shaded at 6. You have an open dot there. So these are the numbers that are bigger than 6, greater than 6. And this is how you would write this in, say, upper elementary school, or, whenever you learned it. X is greater than 6. Now, we're going to learn a little bit fancier way to write that, and I'll show that to you. You start out with X. This is called set builder notation when I do this. X is greater than 6. And you simply put some, fancier stuff around it. Let me show you what that stuff looks like, okay? You're going to repeat the variable and then put a line like that, a vertical line, and then set bars. And that changes that into what you'll use in upper division math in high school or early college, set builder notation. You'll see this a lot. Now, the way you read this is you say the set of all x's, and when you get to this little bar here, you read it such that, and it's easier to understand if you leave the such out, so I'm going to read it that, okay? So what we have here is the set of x's that are x's greater than 6. So you just kind of build the set by, first of all, telling it the general category of what you have. You're dealing with x's, and then you narrow it down. We're only dealing with the x's that are greater than 6. So that's called set builder notation, and it's actually not a lot different than you did in elementary school. If you look at the stuff in orange, you just add that to what you used to do earlier in your career. Okay, now that is a little bit weird for you, so what I'm going to do is just take a little bit of a pause here, and I'm going to show you another application of this. Let's say that you had this set of animals such that they are warm-blooded. Hang on, my stylus is acting up. Warm-blooded. They have hair. They give live birth. They feed their young with milk. And they're vertebrates. Okay. So as soon as I get to this category here, animals, I know that the general category is animals, and I'm not talking, for instance, about oak trees. When I get to the rest of these and I say such that, I know that I'm narrowing it down. These animals have to have warm blood, hair, like they give live birth instead of eggs. They they suckle their young with milk, and they're vertebrates, okay? And you may recognize that this set has got a name. It's called the mammals. And we are part of that set, okay? But that's just an application of this symbolism, and hopefully that helps you understand a little bit how that works. Okay, there's another way of doing it, and this is called interval notation. And what you do is let me start from scratch here. You start by giving the borders. This set starts at 6 on the left. So let's put 6 on left of a comma. And then the right-hand side of this interval doesn't actually stop. You can see it goes forever that way. So what we do is use a symbol for infinity. When it goes forever to the right, you use infinity. And always put the smaller first, 6, and the bigger second, infinity. Then you tell me whether it's an open dot with a parenthesis or a closed dot with a square parenthesis, okay? So since the 6 is not included, we're going to use the open parenthesis, and that means it's an open dot. And infinity is very slippery. When you try to get to infinity, every time you think you got it and you can put a cage around it and include it, somebody's going to say, no, infinity is further to the right. So with infinity, you always put the round one. Now, if you're going to the left forever, it would be negative infinity. And that would obviously be the smallest number possible, so you always put that on the left side of the comma when you do that. Okay, so let me give you some examples of this. All right, so what we have here is a closed dot at -3, and it's shaded between there and 1, where you have an open dot. So the smaller number first, the bigger number second, and we're going to include the -3 because of that closed dot and not include the 1 because of the open dot. So that's the interval notation version. I'm not real pleased with how I wrote that, so let me fix it. And then the set builder notation, you first of all write in between -3 and 1, and you may not be familiar with this, so I want you to learn this right now. To do in between, you put your variable in between two less than signs. Let that sink in. You must use less than signs on either side. Don't turn it around, make greater than on 1 or less than on 2 greater than signs, but it's less than on each side. You put your smaller number down here and your bigger number up here, and then you might have to modify it. We're going to include the -3. So if you look at just this part of it right here, that says all those numbers are to the left of 1, but they don't include 1, which is true if you're looking at this part right here. And those same numbers are bigger than -3. You have to read it backwards. If you choose to say the other way, it's -3 is less than x. But if you want to think of it more easily, you think x is bigger than -3. In other words, to the right. Okay? But just remember less than there, and put your variable in the middle, and that's how mathematicians write in between values. So for instance, most high school students have an age that's between 14 and 18. And there are exceptions, but that's that's how you could express that idea. Okay? So let me do another one here, and I'm going to start by highlighting or doing a graph here. It says the x values such that, oh, I forgot to put the set builder notation, so let me change to an orange pen here and put, oops, too thick. Let me try that again. All right, I'm going to put a bar and repeat the variable and put the braces around it, and that's the set builder version. Okay, that second line, x is less than or equal to 4. We put a closed dot at 4. And less than or equal to is shade this way. We have a left bound of -infinity and a right bound of 4. So left bound of -infinity and right bound, notice the order I'm putting them in with the smaller one on the left. You always use a round bracket for the -infinity. And since we have a closed circle there, the 4 is actually part of the graph. You indicate that with a square bracket. Okay, another one here from -infinity to 2. -infinity is all the way over here. And 2 is over here. And since there's a square bracket there, I need a closed dot. And we're shading this way. Okay, so the graph is done. And those are the points that are less than or equal to 2. And we're just simply going to make set builder notation out of it by putting the extra stuff on. Okay, the last one here, and this will be the last one on this video, and then I'll do the other parts of this video, and I'll break this up and do parts C and beyond on another video. Okay, if you have all real numbers are things like 1 and 2 and everything between 1 and 2, decimals, fractions, and it includes negatives, you include 0, and you include really, really small numbers like -10 billion, and you include really, really big numbers like negative or positive 3 trillion and so forth. All real numbers. There are actually numbers that are not called real numbers. They're called imaginary numbers. You'll learn those later in this course. But this line is completely shaded in, And what I just did is I represented in one tiny little graph all of the numbers you've ever used in school up until now. Assuming that you haven't worked ahead and learned about imaginary numbers, which is part of this course. You'll learn it, and it's my favorite part. All right, how do you do this on the set builder notation? Well, there is actually no set builder notation version. You just say all real numbers. Now, there's a symbol for that, and you should learn this, and you're welcome to use it. You make an R with a double spine, like that. Make a very pronounced double backbone R, and that means the same thing. It means all real numbers. And so you'll see me use that a lot. I just put a double backed R, and that means all real numbers. The X is any number you want. Now, the left-hand side of this is negative infinity, and the positive side is positive infinity. So you just go negative infinity to positive infinity, and once again, you always use round ones on either of those symbols. Okay, that does it for parts A and B, and I'll pick up on another video for some of the other stuff.